think this was like 9 megs. I didn't think that was too huge, but if it is on your end, let me know, and I can try to make turn this into a JPEG instead of a PDF. But anyway, so a lot of repetition in the evens as opposed to the odds. One problem that I thought was kind of interesting was the number 110 problem, which if you have to get your car smogged, this is kind of a little bit of the process. Now, granted, the people doing the smog test at the gas station, they have a computer, so they're not doing any of this math, but this is the math that the computer is running. And that was the one problem that I thought of all these, it was pretty tricky. Oh, darn it. Okay, let me flip this over that way. Okay. And then, so I'll just kind of do a cursory review. So here, they tell you the degrees per second. So I wanted to find the distance in that amount of time. Okay, so I just used the proportion out of 360, the arc out of, okay, and that got us the inches. And since that was the inches per second, since the unit of time was degrees per second, we don't have to do anything extra. Okay, and here it's often used either to convert to radians to use these formulas, and so that's what I did here. And the same thing here, the difference is looking for the central angle. Now be careful, because if you use this formula, the central angle is in radians. So that might be something we forget, so that's what I got here. And then if you want to convert to degrees, that's what I did here. That's probably a little less than 50. So my picture isn't to scale at all. Okay, and here they give you the meters of distance along the arc in 20 seconds, so you can convert to linear velocity immediately, which is distance per time. Okay, so now what we want to do is find out the number of revolutions. So every circumference is worth 1. So how many circumferences go into this 1/4 meter? That's why I'm dividing. Okay, so now we got revolutions per second, and every revolution is worth 2 pi radians, so we're multiplying. And so then we get this. And kind of similar thing here, except they give you revolutions per second. So I multiplied the circumference, got the distance per second. And now they want you to find out the miles per hour, so I converted, and that's how you got that. So this was a similar problem to the distance between Memphis and New Orleans, except here it's Charleston, West Virginia, and Charleston, South Carolina. Same name, but 2 different places in the United States. So what you do is you convert these to the degrees, and then you can subtract. That gets you the central angle, and then you can set up the proportion out of 360 to find out the arc length, the distance between the 2 cities. Okay, and here we got the Earth revolving around its axis, in addition to it tilting, because the Earth tilts closer to the sun during the summer months in the Northern Hemisphere and away from the sun during the winter months. And so after the winter solstice, which is December 21st, we're now starting to tip back. And so this causes all the weather patterns. But anyway, in the Northern Hemisphere, you got a smaller circle that you're revolving around. So the interaction with the sun is a little bit different the further north you go for that reason. And so we just find the distance around that circle. That's every 24 hours. And so you can just convert this to miles per hour that quick. Okay, and here's the Earth going around the sun, very large distance. Incidentally, I think it takes the light of the sun to reach the Earth in 7 minutes. I think it's 7 minutes. I didn't do the should have done the calculation before I said that, but It's kind of interesting, I think. Anyway, so we want to find the distance. So one revolution takes 365 days, multiplied the circumference, and then we want to convert from miles per day to days per hour, and then miles per hour. So you can see that's pretty fast, and here we are on the Earth, traveling around the sun. We don't really feel that miles per hour, but as Earth is hurtling through space in this relatively elliptical orbit, that's the miles per hour. Okay, now here's the Ferris wheel. So they gave you the radii in feet, 30 feet, and then one revolution every 70 seconds. Okay, so first we want to get radians per second, which is called angular velocity. So I multiplied 2 pi because one revolution is worth 2 pi. So 2 pi radians in 70 seconds, and then we can simplify that to get the radians per second. And then linear velocity would be based upon distance per time. So one circumference is one revolution. So that's why I'm doing the circumference divided by 70. And then that gets us the distance per time. Okay. Now 110, to me, since they wanted us to use the information in A and the information in B to basically find either miles per hour or revolutions per minute, I thought it'd be easier, but let's go ahead and create a formula for miles per hour, since we're going to be given revolutions per minute and we want to find out how many miles per hour that is, or we're going to be given miles per hour and we want to use that to find out the number of revolutions per minute. So I set up this cancellation to create a formula that will go from revolutions per minute to miles per hour and vice versa. Okay, so here's how I set it up. Now, one circumference is one revolution, so you can go from revolutions to circumference right here, which is in inches. So it's really converting to inches, and then inches to feet, feet per mile. And then I just put the numbers in, simplified that, got this formula. Now it's a lot easier. Now you just replace the R with 480 and solve for the miles per hour. Replace the miles per hour with 80 and solve for R. And so for part B, just multiply the reciprocal. So it's a lot easier if you construct this formula and then use that. It's a lot easier. Okay, and then here, they gave you this arc distance. Oh, I remember now what this problem is. So on the east coast of Florida, when the light hits, when you first start seeing the rays of the sun, the west coast of Florida is still dark. So how much time is it going to take for the light on the east coast of Florida to get to the west coast of Florida? Well, that means this distance of 90 had to have occurred. And so since we know the rotation is 24 hours, we can set up this proportion. 90 out of the total circumference would be how many hours out of 24? And so you do this, you get the hours, and it's less than an hour. So I want to convert that to minutes, so that's why I multiplied 60. And then I took the leftover decimal, multiplied to 60 to get the exact minutes and seconds. So if you're in Miami, it's going to take about a little less than 6 minutes before the light reaches Tampa. Now, I think the actual town in the problem was Naples, Florida. Okay, now, what we call a nautical mile is the distance of 1 minute. And the reason why that is because back in the days of ships traveling across the ocean, they didn't have radar. They had to use the sky. They had to measure how they were traveling based upon looking at the sky. And so they would measure angle change from a particular fixed constellation. It's usually the North Star, but not always. And so if they traveled a minute of degree by using the measurement of a fixed star, that would be called a nautical mile because it was practical. Okay. They didn't have radar, so they couldn't calculate distance in the open ocean any other way by noticing, okay, we just travel a minute from where we were an hour ago. That's called a nautical mile. So how much distance is that actually? All right, well, we know 1 minute is 1/60th of a degree. All right, and so I went ahead and converted that to radians. And then I used the proportion out of 2 pi, how much distance out of the total circumference, and rearrange that. And so you can see if you wanted to just use this formula, we already have radians. And so the radians times the radius, and we can do it that way too. So a little more than a regular mile. So it's not exactly a mile, it's actually more than a mile, a little more than the regular mile. Okay.